Picture a scientist holding like a perfectly clear, delicate petri dish, just a few drops of liquid, right?
Right. Perfectly controlled, totally visible little environment.
Exactly. Now take that image and completely shatter it.
Yeah.
Because the reality of how we actually get life-saving medicines or, biofuels and synthetic materials to millions of people, it does not happen in the palm of your hand.
No, not at all. It happens inside these massive multi-story steel vats. I mean, we are talking about a boiling, chaotic, highly pressurized microbial soup on a scale of tens of thousands of liters.
Yeah, and the jump from a few cells in a lab incubator to a commercial scale facility is, well, it's arguably one of the most brutal hurdles in modern manufacturing. You're basically trying to domesticate microbiology.
Exactly. You're forcing it to survive the unforgiving laws of industrial physics.
So have you ever wondered how engineers actually manage to design and control these giant artificial habitats without everything just crashing? Okay, let's unpack this.
Yeah, let's get into it.
Our mission for this deep dive is to decode a stack of highly technical engineering notes on biochemical reactors, specifically focusing on floc and film reactors. We're going to uncover how chemical engineers map out these environments, moving from the simplest batch pots all the way up to incredibly complex, continuously looping biofactories.
Which is fascinating because we'll be exploring the underlying fluid dynamics, the economic trade-off, and the physical limits that dictate how these facilities are built. It's a constant tug of war, really.
A tug of war between what the biology naturally wants to do and what the mechanical equipment can physically handle.
Right.
So whether you are catching up on industrial engineering or you're just intensely curious about the physical mechanics of the bioeconomy, this deep dive is going to give you a serious aha moment about the invisible choreography happening inside those massive steel tanks.
And to really understand the continuous high-tech systems, we first have to look at the absolute foundation of biochemical engineering.
Right, the batch reactor.
Exactly, the single pot method. You basically put the inoculum and the substrate into a sealed tank, and you just let the reaction run its course.
And the governing principle here is pretty straightforward mass balance.
Yeah.
You look at what goes in, you subtract what goes out, add what is generated by the reaction, and that equals your total accumulation.
Yeah.
So NN minus OUT plus GEN equals ACC.
Right. But in a pure batch process, once you close that lid, nothing else goes in and nothing comes out until the run is completely finished.
Which means the IN and OUT variables are just zero during the actual operation.
Exactly. The entire process becomes this isolated dance between generation and accumulation. The substrate steadily drops as it's consumed, while the biomass and your target product accumulate.
But there's a really fascinating illusion of volume here that the sources point out. Because when you walk into a plant and see a massive cowering fermenter, your brain immediately assumes it is filled to the brim with liquid.
Oh, yeah, but the actual liquid volume hosting the biological reaction is only a fraction of the total space inside that tank.
Right. The total fermenter volume, which engineers call V sub F, actually consists of three distinct physical spaces. You have your working liquid volume, just V.
Plus the gas holdup volume, V sub H.
Yeah, and the headspace volume, V sub HS. So why do we need all that extra space?
Well, if you are running an aerated process, you are constantly sparging air into the bottom of the tank. And those bubbles displace a massive amount of liquid as they travel upward, which is your gas holdup.
And then there is the headspace at the very top of the tank. Yeah. Why is that headspace so critical? I mean, why can't we just maximize our yield by filling the tank to, like, 95% capacity?
Because you desperately need a disengagement zone.
A disengagement zone.
Yeah, the liquid has to separate from the exhaust gas. If you filled the tank to the absolute brim, the moment you turned on the aeration and the agitator, the gas holdup would expand the liquid volume.
Oh, wow.
And you would have a foaming biological disaster blowing right out of your exhaust valves and ruining the entire facility.
So a significant portion of your expensive steel tank is literally engineered to hold nothing but froth and air.
Exactly. It's non-negotiable.
Now, alongside this physical footprint, we have to look at the operational clock. Running a batch reactor is governed by the concept of cycle time, T sub C. It is not just about the biological reaction, time like how fast the cells can multiply.
No, if you build your financial models purely around the specific growth rate of the biology, your factory will go bankrupt.
Right. I was thinking about this like running a restaurant.
Oh, that's a good way to look at it.
Yeah, if you want to know how many customers you can turn over in a night, you can't just calculate how long it takes the chef to physically cook the steak. That's your biological time, T sub B.
Right. The cooking is just one part.
Exactly. To know your real operational cycle time, you have to account for seating the guests, which is your filling time, T sub F. You have to account for clearing the tables and processing the payment, which is your emptying time, T sub E.
And then, crucially, you have to completely scrub the kitchen, bleach the counters, and prep for the next day.
The service time, T sub S.
Yep. The industrial clock wraps filling time, emptying time, and service time entirely around that core biological event. And in a pharmaceutical or food-grade environment, that service time involves draining the tank, running clean-in-place protocols with caustic chemicals, flushing it.
It's a massive undertaking.
It is. You have to pump high-pressure steam through the entire system to sterilize it. That can take hours, sometimes days. Time is money, and if your service time is too long, the biological efficiency of your incredibly engineered microbes is completely wasted.
So if you have a perfectly running 10-liter benchtop reactor and you've optimized that cycle time, the obvious business move seems to be scaling up. Like, why not just build a monolithic 50,000-liter tank and multiply your output?
Well, that introduces the scale-up conundrum. This is where biological ambition hits the harsh reality of physics. When engineers attempt to go from a pilot scale to a massive industrial scale, they typically face two design philosophies.
Right. The first is fundamental kinetic design.
Which requires mapping out absolutely everything. You need to mathematically define the biological rate coefficients, the liquid phase mass transfer coefficients, and the characteristic sizes of the cell flocks.
Basically, you would need to perfectly model the internal hydrodynamics of a massive turbulent system.
Which is computationally and practically almost impossible to get right for a complex biological broth. Because of that, the industry heavily favors the second approach, the scale-up principle, based on constant power per unit volume.
And the logic there seems sound on the surface, right? If you have a small, perfectly mixed tank, every drop of liquid acts identically. To build a bigger tank, you just pump in proportionally more mechanical power to spin the agitator, and theoretically, the fluid should behave the exact same way.
What's fascinating here is how the fluid itself actively resists that mechanical power. Ideal mixing is a total myth at large scales. You can easily maintain geometric similarity like building a tank that looks identical but larger, but achieving hydrodynamic similarity is exceptionally rare.
Because many of the complex suspensions used in fermentation exhibit pseudoplastic behavior. They are non-Newtonian fluids, meaning as the cell density grows, the viscosity of the liquid actually falls when the shear rate increases.
Right, the fluid actually changes thickness depending on the mechanical force applied to it.
So think about stirring a massive, incredibly thick pot of stew. Right near the spoon or the impeller blades at the center of the tank, where the mechanical force is immense, the shear rate is high.
And because it's pseudoplastic, the viscosity plummets right there. It feels thin and fluid.
Exactly. But out at the furthest edges of the massive pot, near the cooling jackets, the fluid is barely moving. The shear rate is practically zero, so the suspension stays thick, viscous, and sluggish.
That creates a violently uneven power distribution across the tank.
Now, let me push back on this, because it seems like there is an incredibly obvious engineering solution here. If the outer edges of the tank are thick and sluggish, why are we tiptoeing around this? Just drop a massive marine impeller in there, hook up a jet engine of a motor, and thrash the entire volume so violently that the whole thing is forced to become thin and perfectly mixed. Problem solved.
I mean, you could absolutely do that if you were mixing concrete. But you are dealing with living cell flocks. If you crank the mechanical power high enough to achieve perfect mixing out at the tank walls, the shear forces near the impeller blades become catastrophic.
Oh, because it's too violent.
You will literally rip the cell membranes apart. You are effectively blending your microbial workforce to death.
Wow. So you were completely trapped. You can't understir it because the edges die, and you can't overstir it because the center gets pulverized.
Exactly. And that alters the entire reaction. Because of this uneven power distribution, the mean particle size of the cell flocks changes depending on their physical location.
Right. A microbe caught near the impeller is experiencing a high shear world with massive oxygen transfer and fresh nutrients. But a microbe drifting near the wall is suffocating in a thick, stagnant, nutrient-poor dead zone.
You no longer have one predictable batch. You have millions of chaotic, interacting microenvironments.
So we can't build a single megavat, because physics literally won't let us stir it safely. To keep production flowing without creating those dead zones, engineers have to rethink the geometry. They network smaller tanks together.
Which is why you rarely see one monolithic pot in a modern facility. You see industrial choreography.
Let's talk about that choreography. The first arrangement is parallel processing. You run multiple batch reactors side by side, but you stagger their operational phases.
Right, so while Tank A is in the middle of its long biological reaction, Tank B is filling, Tank C is emptying into the downstream processing line, and Tank D is being sterilized with steam.
It is a really clever way to create a continuous downstream output from a series of discrete, interrupted batch processes.
It is, but it introduces a severe logistical vulnerability. If that service time gets delayed, say a valve sticks during the sterilization of Tank D, the whole rhythm is completely thrown off.
Yeah, the incoming feed has nowhere to go, and the finished product from Tank C is waiting to be processed. To prevent the entire factory from stalling, engineers have to build in buffer volumes.
Which are essentially holding tanks just to park the liquid while it waits for the next available step in the sequence. And chief financial officers absolutely hate buffer tanks.
I bet they require floor space, they require their own cleaning validation, they consume capital expenditure, and they do not produce a single drop of product.
They are purely an expensive insurance policy against logistical bottlenecks.
So another choreography method is series processing. Instead of side-by-side, you chain the batches together sequentially. A smaller reactor is used to grow a dense population, which then acts as the seed for the immediately larger reactor in the chain.
This is great because it allows you to build up your working volume gradually without diluting your initial inoculum into a massive tank where they might struggle to establish themselves.
But the timing here is a total knife edge. This series method only efficiently utilizes the total volume of your plant. If the batch cycle time, T sub Bs, and the final microbial concentration, M sub S, are exactly identical across the entire chain.
Right. The smaller reactor has to finish its growth phase and hand off its contents at the exact millisecond. The larger reactor is clean, empty, and ready to accept it.
It is a high-stakes relay race. If the baton pass isn't perfect, the biology in the smaller tank will start to enter the death phase while waiting.
Or the larger tank will sit idle, burning operational cash.
And then we have the fed batch system, which is incredibly common. Instead of sealing the tank, you continuously trickle in highly concentrated fresh feed. You are deliberately diluting the reactor content over time to match the growth of the biology, keeping the concentration perfectly stable.
Yeah, fed batch is a staple in the industry.
So what does this all mean? When you look at all these complex arrangements, parallel arrays, sequential series, fed batch trickles, merely taking the volume of one theoretical megabatch and splitting it across multiple smaller tanks does not magically boost your overall biological productivity.
No, it doesn't. You are just changing the spatial arrangement to manage the fluid dynamics.
Precisely. You are multiplying your capital costs. You are buying miles of extra piping, dozens of extra sensors, and vastly complicating your automation programming, purely to sidestep the physical limits of mixing.
A choreography has to be flawlessly timed, or it is just a massive sinkhole for capital.
Which naturally drives engineers toward the ultimate goal. Because even a perfectly timed parallel array still has inherent downtime. You still have to drain tanks, pump in steam, and cool them back down.
So the dream is to never stop. What if we continuously push fresh broth in and simultaneously extract the finished product out forever?
That brings us to the pinnacle of reactor design, the continuous stirred tank fermenter, or CSTF.
In a continuous system, everything revolves around the average residence time, T sub R.
Right, which is just the liquid volume, V, divided by the flow rate, F. That tells you, on average, the lifespan of a single drop of liquid inside the reactor.
It is the master lever that dictates the entire pace of your operation. But pushing that lever introduces a brutal, unforgiving trade-off between the flow rate and the concentration of your biomass.
And this trade-off leads to the most terrifying phenomenon in continuous operations, the washout cliff.
It really is the scenario that keeps process engineers awake at night.
Picture a treadmill. You have your continuous reactor humming along and you want to maximize your factory's output. So you turn up the flow rate, you're pushing more substrate in and extracting more liquid out. This is like hitting the speed up button on the treadmill.
Because the faster you run, the more calories you burn, or the more product you harvest.
Right. But the microbes have a biological speed limit. Their maximum specific growth rate is fixed by their DNA. So if you turn that treadmill dial up just one notch too high, your legs physically cannot cycle fast enough to keep up with the belt.
You don't just jog a little slower, you get violently launched off the back of the machine.
Exactly. That is the mechanics of washout. The moment the liquid flow rate exceeds the maximum reproduction rate of the biology, Every new cell is swept out of the exhaust valve before it has a chance to divide.
It is not a gradual decline in yield. It is an absolute cliff. The biomass inside the tank plummets, the unconsumed substrate spikes to match the inlet feed, and your entire productivity instantly hits zero.
You are just pumping expensive food straight through a sterile steel pipe.
And the agonizing reality for process control is that peak economic productivity exists right at the edge of that cliff.
Right. To make the facility profitable, you have to run the flow rate as dangerously close to washout as possible without tipping over.
It's a constant high-wire act. The slightest deviation from perfect ideal mixing can trigger a massive crash.
Because if a tiny pocket of fluid isn't mixed properly, or if a rogue film of microbes starts adhering to the free surface of the liquid and alters the internal hydrodynamics, the whole system loses its balance and gets pushed over the edge.
So the question becomes, how do you cheat the physics?
Here's where it gets really interesting. How do you crank the flow rate to achieve astronomical productivity without washing away your microbial workforce?
You introduce a continuous stirred tank fermenter with biomass recycle.
Yes, you trap them. The engineers install a separator right at the exit valve of the reactor. This could be a specialized filter, a sedimenter, or an industrial centrifuge.
And the entire trick relies on a massive disparity in physical scale.
Right. Inside that broth, you have your substrate and your target products, the valuable molecules you want to harvest. They are incredibly tiny on the scale of 10 to the negative 8 meters.
Super small.
But the working biomass, the cell flocks, are comparatively huge. They're on the scale of 10 to the negative 6 to 10 to the negative 3 meters. That is like comparing a handful of marbles to a cluster of skyscrapers.
And the separator exploits that vast chasm in scale. It acts as an invisible, highly selective net.
The tiny product molecules are so small, they slip right through the separator and flow completely out of the system as your harvested yield. But the massive microbe flocks hit the net.
They are caught, pulled out of the exhaust stream, and mechanically pumped right back into the front of the reactor via a recycle stream.
Engineers control this mechanism using two critical parameters. The recycle rate, tau, which is how much of the total exit volume is diverted back, and the recycle concentration factor, gamma.
And for this cheat code to work, gamma has to be greater than 1. The biomass returning to the tank has to be highly concentrated. You are actively squeezing the liquid out and sending a dense, incredibly potent sludge of microbes back to the front lines.
If we connect this to the bigger picture,
the implication is world-changing for manufacturing. Biomass recycling fundamentally severs the liquid's residence time from the biomass's residence time.
Because in a normal continuous tank, the water and the microbes are chained together. They leave at the exact same speed. But with the separator acting as a bouncer at the exit, you can flush the liquid feed through the reactor at a blinding speed.
You can turn that treadmill up to an absolute sprint, achieving massive volumetric productivity.
Because the liquid races through, but the actual working organisms stay safely trapped inside the reactor indefinitely. They bypass the washout cliff entirely because they are never permitted to leave the system.
It is a stunningly elegant mechanical solution to a biological speed limit.
Okay, let's recap this massive journey for everyone. We started by cracking open the simple batch pot, revealing the critical hidden volumes of gas holdup and headspace required just to keep the liquid in the tank.
Then we explored the viscous pseudoplastic nightmare of scaling up, where stirring too little starves the edges and stewing too hard blends the center.
We observed the economic realities of industrial choreography, chaining tanks in series and parallel to sidestep the physical limits of fluid dynamics. We stared over the terrifying cliff of washout in continuous flow systems, sprinting on that biological treadmill.
And finally, we solved the ultimate bottleneck by employing a microscopic sieve to recycle the cell flocks, totally decoupling the fluid mechanics from the microbial lifespan.
You now possess a deeply technical mental blueprint of the invisible industrial biofactories that are quite literally manufacturing the physical materials of the modern world. You understand the engine underneath the bioeconomy.
But, looking at this perfectly optimized continuous loop system with a biomass recycle, it brings up a wild, almost philosophical concept.
It absolutely does.
It is a thought worth leaving you with. Consider the reality of that recycled continuous fermenter. Because of that mechanical separator catching the cells and throwing them back in, those microbes are not living a normal biological life cycle.
No, they might remain trapped inside that pressurized steel tank for thousands, perhaps tens of thousands of generations.
constantly dividing while the liquid environment artificially refreshes around them. They just keep cycling, living, and dying in that high shear steel vortex.
And we know that evolution is driven by survival and adaptation to environmental pressures. So how might these microbes biologically mutate over time?
Right, they are trapped in a perfectly engineered, highly turbulent, constant food environment that bears absolutely zero resemblance to the natural world they evolved in.
So are we simply harnessing these organisms to manufacture our products? Or by designing these extreme inescapable artificial habitats, are we actively forcing a completely new industrial evolutionary path?
It makes you wonder.
From the pristine, perfectly contained little petri dish to an inescapable engine of forced evolution. Thank you for joining us on this deep dive into the architecture of biochemical reactors. Keep questioning the invisible systems around you and stay insanely curious.